Hi, I'm Brendan, here with Samba, Diana, and Meng. We're part of Group A19, and we're here to talk to you about variance and Chebyshev's inequality today. However, before we begin, if you want to see this and other videos about discrete mathematics, go visit www.noatom.com, and you'll find a lot of useful videos there. Now then, our topics for today will be variance, which will be presented by Samba, Chebyshev's inequality, which will be presented by Diana, and then lastly, Ming will present us with some problems and examples. Now then, here to talk about variance is Samba.
Hello everyone, I'm Samba and I'm here to talk about variance. First, to define variance, we can say it's just the measure of how far apart points are, meaning how spread out they are. And it's also a descriptor of the probability distribution, and in that sense it describes how far the numbers lies from the mean, which is just the expected value. And this is important because for a lot of researchers, this is how they define the validity of their data points. It's also used in other things, just like in 203, it's used to define what range the people are getting A's and what range the people are getting B's. So it's used in everything. Now, if you say just take a random variable x, and the mean, which is written here as mu, is also called expected value, and the variance, by definition, is just the expected value of the square difference between the variable's realization and the variable's mean. And in math terms, it's just written as this, as e of x minus mu, the whole thing squared. The definition is written here on top, which is the definition that we know in class, which is e of x squared minus e of x, the whole thing squared. But it's actually the same definition when you derive it. And we like this definition because it is still valid for random variables that are discrete, continuous, or even neither, or a mix of both, like discrete and continuous. That's why it's a very complete definition, and it holds true no matter what kind of distribution you have. So here we have e of x minus mu squared, and it's just the same thing as the math that you learn in middle school or high school, like a minus b, the whole thing squared. It's just a squared minus 2ab plus b squared. So in this case, if you just do a normal distribution, you'll have e of x squared minus the 2 of mu and e of x and mu squared. And that's just derived as this, as since mu is just e of x, it'll be 2 mu squared plus minus 2 mu squared plus mu squared. So at the end, you're going to end up with e of x squared minus mu of x, which is where the definition really came from. And that will be is called in English or in regular terms as the mean of squared minus the square of mean.
Hi everyone, this is Diana, and I'm going to talk about Chebyshev's inequality today. First, let's look at the theorem statement. So let x be a random variable on a sample space S with function p. If r is a positive real number, then we have the probability of the events which are having values that are greater than the expected value. The probability of this is less than or equal to the variance divided by r squared. And we're going to prove that. So first, we're going to define A, B are the events that have values greater than or equal to the expected value. And then we have we know the variance of x will be the sum of the difference between the value of an event and the expected value, and the whole thing squared times the probability of that event. And now we're going to split it up because we know any event S will either be in the A we define or not in it. So we split it up, we got the two sums. And then we know we simply just remove the second part, this part of the sum, this sum. And so we know this whole thing must be greater than or equal to this single guy. And then we know, because of the event A we defined, we always know that any event in A, the value of it must be R greater than or equal to E of x. That means the difference between the x of S, which is the value of the event, and the expected value must be greater than or equal to R. So that means the whole thing squared is going to be greater than or equal to R squared. And then we just factor out this part, let it being R squared, and leave the part P of S and sum it up. So now we have this equation greater than or equal to R squared times the sum of the probability of each event S, which belongs to the space A. And then we know the sum of all the probabilities will be the probability of this whole space. So this equation is equal to R squared times P of A. And then we got V of x is greater than or equal to R squared times PA, which is the probability of all the events that have values R greater than or equal to the expected value of x. Then we just simply divide both sides of the equation or inequality by R squared. Then we got V of x divided by R squared is greater than or equal to P of A. And then we got this theorem proved. And now Mingming is going to talk about the examples of both Chebyshev's inequality and the variance.
Hi everyone, I'm Mingming Jia, and I am here to give some examples of variance and Chebyshev's inequality. So first, let's take a look at a variance example. So let x be the discrete random variable with the distribution as follows. And let's work to find the variance. So first, the first line gives the equation for finding variance. One of the variables we need to find is mu, which is the same as the expected value of x. So to find that, it's going to be the probability of the first value times the first value, plus the probability of the second value times the second value, and so on. And as you see from that, we'll get that mu equals 12 over 7. Variance will now equal 0 minus 12 over 7 squared times the probability of that first value, which is 1 over 7, plus the second value, 1 minus 12 over 7 squared times the probability of the second value, which is 2 over 7, and so on. And from this, we will receive our answer, which is that variance of this random variable is 1.714. Now let's look at an application for Chebyshev's theorem. Let's find the probability that x will take on a value within 3 standard deviations of mu. Assume a normal distribution. So the equation is that the probability that the x minus mu is less than 3 standard deviations will equal 1 minus the variance of this distribution divided by 3 standard deviations squared. So we know that, looking at the denominator, standard deviation squared is variance. So variance in the numerator and denominator cancel out, and we get 1 minus 1 over 3 squared, which is 8 over 9. So this means that at least 89% of the values of x fall within 3 standard deviations of the mean. Thank you for watching our presentation today, and we hope we were able to clarify some information about Chebyshev's theorem and variance.